Recording in progress.
And I'd like to begin, like every lecture, asking if there are any unclear things. I noticed in the last lecture, there were some comments on YouTube. There was one comment by, I don't know if it was a student in this class, but it said, "This is too much for my poor undergraduate brain." I then asked at which moment in time the crucial step had happened that was too much, but no answer came. So I'm not sure if it was somebody in this class. If it was, please don't be shy. You can also talk to me during the office hours if you don't like to do it in front of others. But again, I do welcome very much any kind of questions, even silly things. Chances are you're not the only one thinking about it, right? And so it always gives me the opportunity to clarify things. And this is, of course, one of my main goals, to make this really crystal clear, right? I'm trying to convince you here of crazy things, right? And we can describe macroscopic properties you can measure with big devices. We can write them in terms of solutions to Schrödinger equation, okay? This is until only a couple of decades ago, this is unheard of. So let's really try to make this as clear as possible. Now, to get back to the topic, we entered chapter 3, and we are dealing here with state functions, okay? So most properties you've been discussing in thermodynamics are indeed state functions. Not all, but many, right? And in particular, when we are dealing with equilibrium processes that occur in equilibrium, so reversible processes, right? We often deal with some of the most important properties are state functions. So in particular, we first discussed the most important of all properties, the energy, and we simply, thanks to having a probability, we can write it down as the statistical expectation value, meaning the sum over all the possible states you have, and each summand is the product of the probability of that state and the magnitude of your property, right? So this kind of sum is abbreviated with this short-term notation here, these funny brackets. And maybe you've seen them also in quantum mechanics. People use it and call it bracket to illustrate bracket, right? So you split the bracket word in two. And the idea behind it is the same. It's also an expectation value. It's the quantum mechanical expectation value. And then you have the classical mechanical expectation value. We use the same symbol, right? It's the symbol for the expectation value. So we use this, we inserted our partition function and our Boltzmann factor, and we then realized that this is just what you would get if you differentiated Q with respect to beta. And so the average energy is the negative of this derivative. Now, you might consider beta to be annoying, you rather operate in temperatures instead of inverse temperatures. And so let's do the little exercise to express it in terms of temperature. I can also write, so it's the same equality symbol, right? I'm just continuing here. I can write this by first differentiating with respect to t, logarithm q, and then multiplying this with the derivative of t with respect to beta. Now, this is nothing else than a simple rule of differentiation, which hopefully you've seen in high school already. It's called the chain rule, right? So if you don't recall, if I have some function f that depends on some other function g that depends on my variable x, and I'm interested in its derivative, I can simply first differentiate f with respect to g, and then I differentiate g with respect to x, right? So in our case, f is the logarithm of q, and g is the temperature. Okay. Now, we have a definition of beta as 1 over kbt. And that, of course, means that if we rearrange, t is nothing else than 1 over kb beta. Okay, that's the same. Just rearranging things. And so if I differentiate my t with respect to beta, I get minus 1 over kb beta squared. All right. Any questions on this? It's like differentiating 1 over x, right? I get a change in sign, and then the higher inverse exponent. So that's that. And then the logarithm of q, this thing has to be derived with respect to t, and that is then something we can simply leave implicit. So what happens then to my derivative, if I insert my my derivative of t with respect to beta, is that I got rid of the sign. I get 1 over kb beta square. And I get the t logarithm q. Now, if I insert again for my beta kbt, then I have 1 over kb brackets 1 over kbt squared dt logarithm q, and that simply gives me kb t squared dt logarithm q. And these are all equalities. Okay, so I like to do this, connect the equalities symbols so you can distinguish where is our derivation happening, and anything that's not connected are intermediate steps I just gave you for clarification. So now on the top, you have it, you have the average energy, it's a derivative with respect to beta. And on the bottom, you have it, it's a derivative with respect to T. And you simply have this prefactor in front, right? So the top one is more compact, is more elegant. And if you're lazy, like I am, you need to write less, right? It's easier to keep the oversight. But maybe the lower hand one is more intuitive or more convenient because you might be more familiar with T than with beta. Right? Either one is fine. Are there questions on this derivative and this derivation? All good? Okay, so this is sort of abstract still, right? How shall we imagine an average energy in terms of this derivative of a logarithm of a partition function? And so it's instructive to now consider an example. And the favorite model system in the world of physical chemistry is the ideal gas law, right? So we consider the ideal gas. Now, the ideal gas, just to recall, is monoatomic. And it has with only translational degrees of freedom. Okay. That means there is no internal, so vibrational. There's no rotational. There's no electronic. There's no spin, and so on, whatever kind of physics you might want to consider. We all ignore and we consider these minuscule billiard balls to be flying around. Yeah. So that's idealized, but certainly you can flip this around. You can, before you criticize it for being so idealized, right? You could ask yourself, if we cannot get that description right, why would you want to move to something more complicated, right? Let's first make sure we get those billiard balls right, and then we worry about molecules. All right. So my partition function is my sum over states J with the Boltzmann factors, right? Now, this state, EJ, contained all the physics. This is the generic one, right? But we only want the translational, and we also only want the partition function for identical, indistinguishable atoms. So same chemical element, if you wish. Right? The closest we can get to that is a rare gas atom, maybe helium, a whole bunch of heliums. So not a mixture of different elements, no physics. And you can show that this can be rewritten. So pure. This can be rewritten as a product over particles. And each particle has its own partition function, small q, right? And so this is for indistinguishable particles, the number of particles factorial because they are indistinguishable. Because they're indistinguishable, I can I have this factorial factor, and because they are all the same, this product is simply the same as number of qi to the number of particles. Okay. Now, this equality here is due to some rearrangement in my exponents, and we will encounter this later. So this will be shown later in the course, to be discussed later on. Okay. So in the case of the ideal gas for identical particles, my partition function for each particle I, and I'm sorry, I don't need the index here anymore. So for each particle I is the same. So I have q to the power of np instead of the product of different particle types. So the small q for ideal gases, we will show later in the course that the small q is 2 pi times m, the mass of the particle, over h squared, Planck's constant squared, beta, our inverse temperature, to the power of the third root times the volume. Okay. Now, this is something we will show later in the course. Now, didactically, you might criticize this, that one should not take results that come up later and use them earlier on, right? But I think it helps to illustrate you how things look like once you want to calculate something and recover something, to check if it's true, right? Or to check if you get what you should get. All right, so this is my small q, and I can now look at the logarithm of q, okay? That's something I will have to differentiate later on. Now, that logarithm of q must be the logarithm of q to the np over np factorial, okay? Let me add these brackets to make sure this is an argument. Now, the logarithm rules tell us that we can split this out. Now, let me do it like this. So my NP is my exponent, of the logarithm of small q minus the logarithm of np factorial. Okay. So my denominator ends up in a negative sign for the logarithm. Okay, so this is basic logarithm rules. And now I don't care about this one because it's not a function of beta. Okay, we will be differentiating with respect to beta, right? So we don't care about any additive term that doesn't contain beta. Now, this means I have NP logarithm of my small q. Now, what's my small q? Is 2 pi times m over h square beta times v minus the other logarithm I don't care about. Now, if you look at this argument, right, the small q here, and again, I'm sorry, the exponent 3/2, we can pull it in front. If I look at this, sorry, so this must happen here. Has to be careful, huh? So we have other terms here which do not depend on beta, right? The volume term, again, logarithm rule, I can split it off as an additional term and a summation, and it's not beta dependent, right? Volume does not contain beta. So we are left with this, and there's this 2 pi m over h square, everything not beta dependent. So again, I can simply say this is minus 3/2 np logarithm of beta. Okay. Now, my averaged energy is minus the derivative of beta logarithm q. Now, there's a minus already, so I get 3/2 np d beta logarithm beta. Okay. And now I finally differentiate. So the logarithm of x differentiated gives me 1 over x. So this is 3/2 np divided by beta. And beta is the inverse temperature. So this is 3/2 kb np times T. Okay. So the average temperature has got to do something with T. Now, what about this prefactor? We can actually look at NP, and this is the number of particles in our ensemble. It's gigantic, right? So we are talking Avogadro's number. So this will be N moles, right? N times Na. Okay. So in other words, I have 3/2 N moles. And now let's put in my Boltzmann constant, 3/8 times 10 to the minus 23 joules per Kelvin times 6.02 times 10 to the 23 per mole times T. Now, if you look at this product, you get 8.31 joules per mole and Kelvin, which is also known as the gas constant R. So what do we have? 3/2 nRT is our averaged energy. Now you might remember from our first lecture in this course, I told you PV is an energy. Right? And here you have it. We derived it. Granted, I gave you this expression up here, but we will see later in the course how we arrived there. Okay. So this tells you that RT, so let's call it like this. Sorry. I can make the whole thing molar, okay? So per mole, I would have my molar internal energy to be 3/2 RT, and correspondingly RT being 2/3 of the molar energy. Now, in the ideal gas case, and now think back about the introductory discussion on classical mechanics, there's no potential energy. All the energy is kinetic, okay? So U equals E kin plus E pot. This is 0. And for this reason, we can write our U as 1/2 momenta squared over m. Okay. This is the kinetic energy of a particle. And now that means for us that the averaged energy is 1/2 m velocity, expectation value of the velocity squared, right? Remember, B equals m times v. And that thing must be nRT times 3/2 see above. And if I rearrange for t, I now see that I have 1/3 mv squared over n and r. So now you have an expression for the temperature in terms of the average velocity squared of your individual particles. There's no such thing in classical thermodynamics. You don't know how to express such a property in terms of individual molecules, right? And we've used the expectation value of the energy and the partition function I just gave you, but in combination with this Boltzmann statistics, that's what you end up with. I should remark once more on the prefactor 3/2 RT. The way, and you will see this later on when we derive this partition function, the way we arrived at these 3/2 was through this exponent here. And when we will show later in the lecture, in the course, how we arrive there, we'll be using Schrödinger's equation in the box. And that's the particle in the box, right? That's akin to the ideal gas. There's no potential energy, right? It's zero. There's no potential except once you hit the walls, right? That's like the volume of your system. And so you can solve the particle in the box in one dimension, what you probably did in quantum mechanics. Did you also do the three-dimensional particle in the box? You did. I see some nodding, right? And so you have quantum numbers in X, in Y, and Z. 3 degrees of freedom, right? And there is a factor 1/2 in there. And that's what you see here. For each dimension, right? For each degree of freedom of tra, of the translation, we have inherited 1/2 RT. Okay, so the dimensionality of your problem fundamentally impacts and dramatically impacts your energy. And then as a consequence, your temperature. We have it, right? That's how you end up with 1/3. So you can immediately see if my particles live only in 2D. Think 2D materials, graphene, graphitic kind of materials, right? 2D materials. The effective temperature in there, it's not 1/3, it's 1/2. Right? 1D material wouldn't be 1/3, would be 1. All right. So These are fundamental observations, but that's what I wanted to say for now with respect to our example of energy, the averaged energy, the internal energy. Are there any questions on this? I hope my writing is not too messy. Let me know if there are symbols you feel unfamiliar with. If that's not the case, then I'd like to go to our next function, our next state function, which would be pressure. Now, some general remarks. Pressure is intensive, like temperature, right? Work and volume are extensive, like particle number, n. There's some simple rules you can use. Typically, if you divide an extensive property by an extensive, you should be getting an intensive property, right? For example, dE by dV. How does the energy change if you change the volume? That's pressure. Now I rearrange this equation, right? And I consider extensive divided by intensive. Then you get something extensive, right? So for example, dE dt gives you heat capacity. And hence heat capacity is extensive. Now on very cold days, today is record cold. For me, I moved only to Canada recently, 2 years ago or so, and this is the coldest day I've experienced in Toronto. If you feel really cold in the morning and you have to walk to campus, you can put some hot potatoes in your jacket to warm up your hands. I don't know if you knew that, but heat capacity of potatoes is huge. Potatoes are fantastic heat reservoirs, right? They will store a lot of heat. Now, the longer your way to the campus, the more potato you should fill in your pockets, okay? That's the meaning of an extensive property. Heat capacity is extensive, right? If it was intensive, you couldn't do that. Now, work is the integral over P as the volume changes, assuming that P is not a function of volume, which is outrageous, but let's just assume. You know what assume stands for, right? I shouldn't use foul language in class, so ask your neighbor. Let's assume that then this is P times delta V. And so you have an intensive and an extensive. So work is extensive. Now, let's see what StatMech has to say about the pressure, right? Well, the pressure you'll observe is our average. Right? So that's the observed pressure, our statistical mechanical average. And in complete analogy to our energy, you now have to consider the pressure your system has in state J. Now, up here, we saw what pressure is. It's the derivative of your energy with respect to volume. So we have Boltzmann's probability times, and by convention, it has a negative sign, dE dV for state J. Again, let's insert our Boltzmann probability 1 over Q, and I pulled the negative sign from my derivative in front, and we have e to the minus beta ej dVej. Now, again, I can do my trick with the chain rule, and I can see that this expression here is identical with pulling my derivative, my differential operator, in front of the summation symbol. If I do that and I differentiate through the sum, I hit again the exponential function. So whatever is the prefactor in that exponent, namely my minus beta, will end up in front of it. Okay. And then I still have to differentiate my energy with respect to V. Oh, sorry. No, that's a... I apologize. This is, of course, EJ, right? Now, again, my apologies. It's just like this, right? So I get, when I differentiate my exponential function, I get the exponential function times the derivative of the energy with respect to E. But my minus beta in the exponent comes in front, so I should divide by it to annihilate it, okay? So minus 1 over beta goes in front, okay? So you can reinsert this to check if it's true, but that's what we have. And so I have two minuses, they go away. I have 1 over beta, 1 over Q, the derivative of J, sum my Boltzmann factors. And now that's, of course, nothing else than Q. So my P is simply 1 over beta Q dVQ. Now, if I have 1 over x times dx some function, that's the same as the x logarithm of the function. So I can still further simplify this, and my pressure becomes 1 over beta dV logarithm Q. Now, recall my energy was minus d beta logarithm q. Now, isn't that pretty? Are there any questions? We've hit the full hour. I'd like to thank you for your attention, and I see you on Thursday.